Hello everyone, I am Sangyeon An. I will be presenting my term project on driver behavior detection. These are the contents of the presentation. Driving accidents due to driver negligence have been increasing. To address this issue, I explored using CNN models to detect and classify driver behavior for future development of in-car cameras. The models I implemented include AlexNet, VGGNet16, and ResNet34, using a dataset from Kaggle. Further details regarding models will be described in the next slides. The dataset categorizes 5 behaviors such as talking, texting on the phone, turning around, engaging in other activities while driving, and driving safely. And the main objective is to analyze and compare the performance of these 3 CNN models in detecting and classifying driver. Here are some random examples of the improper behaviors included in the dataset. These behaviors include talking on the phone while driving, texting on the phone while driving, turning around while driving, and engaging in other activities while driving. You can clearly recognize that these actions are improper in driving. And in contrast, the dataset also includes examples of proper driving behavior, such as driving safely with full attention on the road. Proposed methods are divided by 2 sections. For data processing, first I split the dataset into 75% for training, 20% for testing, and 5% for validation. The original numbers of the datasets in each category are shown in the upper table, and after the split, the numbers of the train, test, and validation sets are shown in the lower table. After that, each image was rescaled using image data generator function from Keras with a rescale factor of 1 divided by 255. Therefore, the range of each pixel values will be within 0 to 1. This normalization is crucial for consistent input to the models. Then I defined the hyperparameters for the CNN models, setting the batch size to 64. The original images are the height of 480 and a width of 640, but resizing the images to a height and width of 240 pixels each. This size is standard for AlexNet, VGGNet16, and ResNet34. Finally, I created input data generators, which will be used for training models and testing and validation as well. The models were implemented using TensorFlow and Keras libraries from scratch in a GPU environment. Each model was trained over 20 epochs. The training process included monitoring the loss and accuracy metrics for each epoch to evaluate the performance of the models. The AlexNet model is trained with total of 24,748,805 parameters, including 5 convolutional and 3 fully connected layers. The architecture uses ReLU activation functions and dropout layers to enhance performance and prevent overfitting issues. These are the snapshot blocks of the convolutional layers and fully connected layers in AlexNet. You can see convolutional layers with the following batch normalization and max pooling, and each layer has its respective parameters such as the number of filters, filter size, stride, and so on. The VGGNet16 model comprises 194,312,261 parameters, following a similar structure with convolutional and fully connected layers. It has a total of 16 convolutional layers. Each convolutional block starts with 2 convolutional layers followed by batch normalization and max pooling layers. Each layer has its respective parameters such as the number of filters, filter size, and stride as well. These are the snapshot blocks of the convolutional layers and fully connected layers in VGGNet16. The ResNet34 model includes 160,858,170 parameters, utilizing residual blocks to improve training stability and performance. Its overall architecture is a little different from previous CNN models. The key feature is the usage of the residual connections that help mitigate the vanishing gradient problem and allow for deeper networks. And at the end, the network applies a global average pooling layer, which reduces each feature map to a single value by averaging for a compact representation. However, each block is similar to the previous models I explained. Each layer has its respective parameters as well. You can see the snapshot blocks of the ResNet34 here. In this experiment section, I will present the resulting plot from each implemented CNN model. Start with the AlexNet. It shows the loss and accuracy trends for the AlexNet model. The loss consistently decreased over the epochs with a dramatic reduction from epochs 1 to 6. Similarly, the accuracy increased significantly during the same period and stabilized afterward. After that, epochs are slightly increased, but it is not considerable as values are not changed dramatically. Here are the loss and accuracy trends for the VGG Net16 model. The loss decreased steadily, with stabilization occurring after epoch 5. The accuracy values also showed a significant rise in the early epochs, followed by consistent levels. The loss and accuracy trends for ResNet34 are depicted here. The model experienced fluctuation in both loss and accuracy during the initial epochs, but eventually stabilized. This indicates some instability in the training process, but still, the loss and accuracy values are good enough. I compiled all the plot results from AlexNet, VGGNet16, and ResNet34 to compare their respective loss and accuracy values based on their validation sets. All the models exhibit similar trends, consistently decreasing in loss and increasing in accuracy values. There are some occasional sudden changes in the graph, but such fluctuations are not problematic as the value quickly converges back to their original values. This suggests that all the models implemented in this research are effective for the specific image processing tasks, especially for handling the driver behavior image detection tasks. In conclusion, all the implemented models demonstrated effectiveness for image processing tasks. However, some occasional fluctuation in loss and accuracy, such as from ResNet34, suggests room for optimization. Among the models, AlexNet was the fastest, followed by VGGNet16 and ResNet34. VGGNet16 emerged as the best overall, balancing training time, stability, and accuracy. And future work involves integrating these models with real-time video capture systems using OpenCV library. This integration could create a real-time monitoring system for detecting and alerting drivers about improper behavior, potentially decreasing car accidents and improving road safety. And this is the end of my presentation. Thank you for listening.